We're going to be talking about a really cool thing today. In some sense, when it comes to the math of juggling, this is one of those results that our people are like, this is sort of like the famous result in math of juggling. And it is a nice result. Let's go back in time. So one of the things we were able to show was that if we have a juggling pattern, that if we look at the average of the throws, so this is this quantity 1 over n times the sum of all those throws, it's a whole number. In fact, it's more than just a whole number. It's the number of objects you're using, balls or whatever it is you happen to be juggling at the time. Now, so what does that say? If I have a valid juggling pattern, then the average has to be a whole number. Now, the question is, well, what about the other direction? Okay, so is it true that if the average is a whole number, we have a juggling pattern? And the answer is definitely no. It is definitely not true. It's not hard to write down examples where this is false. Very simple examples are things, for instance, look at the pattern 5, 4, 3. All right, that's a pattern of length 3. And if you look at the average, it's 4. But this will miserably fail to be a juggling pattern. Well, why? You can actually sort of do it by looking at the beats and say, well, look, suppose you throw a 5, then a 4, then a 3. What would happen? Well, 5, when you throw it, it wants to land 5 beats later. 1, 2, 3, 4, 5. 4 wants to land 4 beats later. 1, 2, 3, 4. And 3 wants to land 3 beats later. And, too many balls coming in at one time. So we run into problems. All right, great. A frustration. It's not true. But is it almost true? And so this was a wonderful question that people had. And in the early days, mathematicians who were jugglers, it turns out there's a really good intersection between the two communities. We're thinking, okay, is it always possible for us to somehow say, maybe we can salvage the situation and rearrange it? As a quick example, what do we mean by salvaging? Well, 5, 4, 3 can't be juggled. But 5, 3, 4, yeah, that is very juggleable. It's easy to check, and I'll let you do that on your own time. So the idea was, maybe it's the case, maybe, yeah, sure, those can't be juggled in the order that I give it to you. Just change the order. So do some permutation, and maybe that can be juggled. So that was a big question, and a lot of people thought about it for a long time, and here's the result. Hall's juggling theorem. The Hall is named after Marshall Hall, who was a mathematician and not a juggler. And indeed, this result, it turns out, had no motivation for juggling. It just was an unintended consequence. This often happens in mathematics. We prove results and theorems, and we do it oftentimes because we like, wow, I want to understand. I want to figure this out. And not really understanding that, hey, there's this nice application somewhere else. And it's one of the wonderful things about mathematics, sort of the unintended consequences of ideas. So we're not going to state what Hall's theorem is. We're going to state the juggling version of it. So what does it say? It says, all right, suppose you are in the situation where your average of these numbers, you have n numbers, take the average, and it's a whole number. Then it must be that there is some ordering of the throws, which is a valid juggling pattern. Not the original ordering necessarily. Maybe you just happen to be lucky and be given a juggling pattern to start with. But the important thing is there's some. Now, be careful with the word some. Don't think of it as like there's just one ordering. In fact, it's possible that there's many. We'll see examples of this. But the key is that it does exist. So, all right, wonderful. Now, you might notice something here about this statement. This is a statement about existence. Some ordering exists. And in mathematics, it can sometimes be the case that we can show, yes, it is true that something does exist, but we don't know how to find it. And it seems strange because you were like, well, wait a second. Don't you have to actually produce something to show that it exists? And it turns out, not always. There are cases where you can show, yeah, things exist, but we're not able to find it. Now, we're actually going to go through and work through a way to actually produce an ordering. So the nice thing is there is a proof, and that gives a nice ordering. And so that's what we're going to work on. All right, good. Well, where to begin? The first thing is to say, all right, let's focus on really just a very simple case. We'll make it an observation. It says, hey, focus on the minimal patterns. In other words, look, all the throws are below n. Remember, we're allowed to add or subtract n, where n is our period, from any of our throws. It doesn't change whether or not it's juggleable. So we can say, let's push it so all the throws are below n. And so it's like, okay, so now our question is there a minimal pattern that happens to have this set of throws? Now, in terms of what we've been talking about, it's like we're looking for a rook placement. In particular, we're looking for a rook placement where we cover these particular numbers. So now we have kind of a slightly different problem that we're talking about, but one where we are a little bit more comfortable. We feel like we have better potential, more tools. And so let's talk about this specific problem. So again, our problem is we have a set of numbers. They're all between 0 and n minus 1. And what we want to do is find a way to put rooks on the board so that the numbers that we cover are exactly the numbers that we have on our list. That's what we want. Well, let's talk about how it can be done. So it turns out there's a very simple algorithmic way that is guaranteed to always let you succeed in placing rooks. And how does it work? Well, it basically says, look, put the rook that you want in the first row that you can, and then resolve conflicts. So let's go through it in a little bit more detail. So we have to put n rooks on the board. And each rook is associated with a number, the number that we want to cover. And so there's going to be n rounds, one for each rook that we want to place. And we say, okay, in our ith round, we're wanting to cover some number t sub I. So, okay, we pick up a rook, we look for the first row. All right, that's sort of somewhat important, and that needs to be noted. It's the first row that's available. And we put the rook so it covers t sub I. Great. Now, there's a catch. And here's the part that's important. It could be the case that there's something in the same column where we put the rook. Definitely not in the same row, because when we said the first available row, available means there's not a rook already there. So we say, is there something in the same column? If there is, take that rook that is in the same column, pick it up, and say, all right, let's find a new home for you. So we're going to move it to the first available row, and whatever number it was covering before, we have it cover that same number in the new row. Aha! We've sort of resolved a conflict. But wait, it might be a new conflict. Okay, repeat. So in other words, do the same procedure. Say, all right, well, if there's a new conflict, pick that new rook up that's conflicting with it and move it to another row and continue and continue and continue. Now, there's a subtlety here. How do we know this works? And the answer is, that's not for this session. We're not going to actually get into the why it works. But what's the subtlety? Well, how do we know we don't get trapped in some sort of infinite loop where we pick up a rook, pick up a rook, pick up a rook, and whoop, back to where we started? You see, just because you have an algorithm for putting things down doesn't mean it's an algorithm that's going to work. What do we need? Well, we need to have it be guaranteed that after so many steps, it will stop. That's where the mathematics comes in. There is actually lots of important mathematics that's done when we look at algorithms, because what we're looking at is saying, hey, is this really going to work? Really? And how do we know it? All right. So we have the idea. It's pretty straightforward. Just always move things to the first available row, resolve conflicts, life is good. Let's actually do some examples just so we can feel we get the hang of it. So we have a board here, and it's a nice board. So let's try some patterns. So let's suppose we want to put the numbers down are 3, 2, 0, 1, and 4. All right, so we have our rooks. We'll bring our rooks over. 3, 2, 0, 1, 4. All right, well, we're not going to quite be able to squeeze them all in, but we'll go along as we need. Okay, so we'll start. Put down our first rook is a 3. Goes to the first available row. Easy. In fact, it's very, very simple to place the first rook. You know, there's nothing on there. There can't be any conflicts. Now for the 2. Okay, so we come over, say, well, where does it go? It wants to go to the 2. And you see, we just placed our 2. There's a rook we already placed before. So we're going to take the rook that was already placed. We know that was on a 3. We go to the next available row, well, the first available row, that is, and cover the 3. Conflict resolved. Aha! We're all at peace again. All right. Next up, 0. So we go to the first row available. Another conflict. So we need to move this one. It's on a 3. Next available row, cover the 3. Done. Okay. Okay, next up, a 1. All right. Well, we go and we put it in the first available row. There it is. So this is the one that we placed. It conflicts with the one just above it. So the one that conflicts, we pick it up, move it, and to the first available row. So, aha, another conflict. Okay, so we're going to pick that one up and move it to the first available row. And we're done. All right, the last one slides right in. Life is good. All right, so there we go. Success. Now, what is the rearrangement that we got? Well, we can read off 0, 3, 1, 4, 2. So that says that the pattern 0, 3, 1, 4, 2 is something which can be juggled. All right, great. Well, more examples, right? The more we do, the more natural it becomes, and the better we'll be able to do. All right, well, let's try something slightly different. 2, 1, 4, 0, 3. Now, you'll notice a couple of things. It's the same set of numbers as we just did. 3, 2, 0, 1, 4, 2, 1, 4, 0, 3. It's just jumbled around. Now, you'll notice that this algorithm is completely what we would call deterministic, which means there's no stage where you have to make a decision. It always tells you what to do. There's no randomness. There's no, well, pick one or two things as you want. No. It always tells you what to do, which means if you feed it a particular set of numbers in an order, it will always produce the same output. Well, what happens if you change the order? And the answer is, well, it depends. It may be the same and it may not. We don't know yet. Let's try it out. This should be good. Okay, so we have 2, 1, 4, 0, 3. So let's start with the 2. Easy. Always can put the first one down. So that's good. So 2's down. Next up, the 1. Conflict right away. Wow. All right, so move the 2 to the first available row. Conflict resolved. Okay, next up, the 4. Okay, put in the 4. Aha, a conflict. We need to move this to the first available row. Still covering the 2. All right, that's good. Done. Next up is a 0 into the first available row. There's a conflict. So we'll move that into the first available row, which is over here. Conflict again. So move that into the first available row, which is over there. And so finally, we have a 3, and nice and easy. Slides right in. So there we go. Well, what's the pattern? What is the pattern? Well, in this case, it turns out it's 4, 2, 0, 3, 1. Okay, good. All right, so something slightly different. Well, slightly different. It's a cyclic shift. Oftentimes, it might be something even more exotic than just a cyclic shift. Well, all right, good. Let's try something else. Okay, 0, 2, 1, 0, 2. All right, this one will be good. I'll tell you why at the end. Okay, here we go. So we start. We put in the 0. Easy, life is good. Next up, put in the 2. Okay, nothing hard there. All right, put in the 1. Okay, so put in the 1. Conflict, so we need to move the 2 to the first available row. Conflict, so we need to move that to the first available row. Okay, now we have our conflict resolved. And 0, well, okay, let's see. First available row, there. There's a conflict, so we need to move the 2 to the first available row, which is there. There's a conflict, so we need to move that to the first available row, which is there. There's still a conflict, so we move that to the first available row. And now everyone's happy. Conflicts have been resolved. Whew, good. And put in the 2 on the end. Doop, right there. And done. Done. Good, good. Now, well, what's the output? Well, our output is 0, 1, 2, and 0, 2. Okay, there we go. Now, I said this is a really interesting thing to feed in. It turns out that among all the things of length 5 you could feed into this problem, this one takes the most steps of conflicts. It's the most conflicted in some sense. Well, you know, we can always resolve these things, right? So, great. Okay, well, we're doing fine on time. Let's do a little bit more. A little bit more. Let's suppose we were to feed in something like 0, 4, 2, 3, 3. Okay? What happens? So, we're getting pretty good at this. So, whoops. So, we'll just go through our paces here. 0 goes in. 4, resolve the conflict. All right, good. The 2 is next. So the 2 comes in. Resolve the conflict. Good. We're doing pretty well so far. So we've gone the 0, 4, the 2. Next up is the 3. So first available row. Okay, resolving our conflicts. All right. Put that over there. And we're good to go. And now, our last one is a 3. And you might say, okay, so pick this up, the conflict, and move it into the first available row. But what's happened? There is no available row, because the only row that's empty is the row it came from. And that row doesn't have the right number uncovered. So wait, I thought this was supposed to work. Well, what do you notice? Go back and look at this, what we put in. 0, 4, 2, 3, 3. What's the average? Well, the average, if you add these numbers up, it adds to 12, but there's 5 numbers. So the average is 2.4, or 2 and a bit. Well, the and a bit says that the average isn't a whole number. And so we failed. Now, why did we actually fail? The part where we failed was that last rook. So you might say, why is it important that the average is a whole number? And the answer is, it's that last rook needs to be placed because there's no extra space available to do your resolution of conflicts. So what you have to do is make certain that when you come to the last rook, that whatever is the available place to put it, because there's only one place, you've knocked out n-1 rows, you've knocked out n-1 columns. It means you've only got one place left. So the only place that's left will be exactly the one you want to cover. That's where being, and the average being a whole number, actually shows up. So this, should never have been put into the algorithm. Okay, one last quick example, and this one really will be quick. 3, 0, 0, 1, 1. All right, so, whoops, almost off the screen there. So what happens? Well, let's do it. 3 goes in, 0 goes in, 0 goes in, 1 goes in, and 1 goes in. There were no conflicts to resolve. Why? Because what you fed it, the thing that you put into it, was actually a pattern that's juggleable. And so if you feed it a juggling pattern, it says, hey, I have no problems here. This is great. And it'll output the same pattern. So it's a really lovely algorithm. And now, where's the math? The math is explaining why the algorithm never gets stuck in a circle. And we'll do that another time. Now, sort of one thing that we should note is that it's possible to have a particular set of numbers which can be rearranged in many, many, many ways. Sometimes just a few. And so keep in mind that the claim about Hall's juggling theorem is not that there's one, it's that there's at least one. So as a quick example, suppose that we took the 7 numbers 0, 1, 2, 3, 4, 5, and 6. All right, great. Well, what happens? Well, if you take those 7 numbers and you ask, can they be rearranged? Well, the answer is yes, because the average is 3. And, well, it turns out that all of these patterns here are valid juggling patterns. And all of them are rearrangements of the numbers from 0 to 6. And no repeats. They're all distinct, which is to say none of them is a cyclic shift of the others. So you can see that even with just a handful of throws, it's possible to rearrange in many, many different ways. Now, I will say this is not just a random, let me pick some set of numbers out of the air. It's strongly believed, and when we have something that we strongly believe, we like to call that a conjecture. And it says, we think the following is true. We don't know how, but we're pretty sure. So what's the conjecture? Well, the conjecture, what we believe is true, is that for n odd, the numbers 0, 1, all the way up to n-1 have the most ways to rearrange. Now, keep in mind that the way that our algorithm works, we only allow our numbers to go from 0 up to n-1. And so we don't allow anything larger than it. If you do, then there's a whole different discussion and it's not interesting. And what's really interesting about this is you can go and you can start doing your counts, and it's true for small values of n. And it turns out that these numbers are related to something else. And what are they related to? Well, they're related to what's called, semi-queens on toroidal boards. Now, at this point, you're probably thinking, you're making some of these words up, right? What's a toroidal thing? What's a semi-queen? So here's sort of the story. So first off, let's start with the idea of a torus. Now, one way we often think of a torus is we think of it kind of a donut shape, where you have this thing going here. But one of the things you can do is you can imagine that you grab a pair of scissors and you cut on one sort of part around. And if you do that, do a cut, what you'll get is you'll get a cylinder. All right, and now take your cylinder and slice down the side, lay it flat, and you'll get a nice little square. So that, in essence, a torus is kind of like a square or a rectangle, depending upon the shape of the torus, that has had the following two things done. Namely, we glue sides together. So we're going to glue this side to that side, and simultaneously, we'll glue this side to that side. So left glues to right, top glues to bottom. So what we can think of happening is we can say, look, instead of having to think about this torus, which is a three-dimensional thing, we can say, all right, I'll think about it as this sort of square where I understand that if I were moving around, that when I exit stage right, I automatically enter stage left. So in other words, I don't go off the board, I just jump to the opposite side and keep moving in. Same thing. If I go up to the top, automatically jump down to the bottom and keep going. So that I can sort of move around, and as I do so, I just hop around as needed. Now, so that's what we mean by toroidal. Now, where do the notions of boards come in? Well, what you can do is you can imagine you're playing chess where you allow things to do a little bit of wraparound. All right, so let's I want to make sure I have an odd number here. So here we have a 5x5 board, and what we're allowed to do is we're just allowed to move around to the opposite edges, right? Top goes to bottom, left goes to right. Now, okay, so that's the toroidal board. So for example, if I were a pawn, normally I can only move one step, but here I say, aha, I can also move to the other side one step. Or I can move up diagonally one step. What's a semi-queen? So a semi-queen is something which is kind of halfway between a queen and a rook. Now, what's a rook allowed to do? A rook is allowed to go any amount on the horizontal or vertical. The queen says, hey, I'll also let you go diagonals any amount. Well, so a semi-queen says, I'll let you go on diagonals in one of the two directions that you can go diagonally. So in other words, let's say I'm allowed to go diagonals this way, but not the other way. So that's a semi-queen. Now, what does all of this have to do with juggling patterns and being rearranged? So let's think about where the semi-queen can go on the board. So if I'm allowed to move, okay, horizontal, vertical, we can see. Let's mark the diagonals. And so we'll just label them. So for example, here I have this diagonal 0, 0, 0, 0, 0. Okay. Now, suppose I have my queen here. Where can it move? Well, on the diagonals, we would say, okay, it can move to those positions. But remember, we can wrap around. So if I were to wrap around to the opposite side, the diagonal would continue in that bottom corner. All right, what if I were, say, the queen were there? Well, again, I can go 2, 2, but now I can wrap around to the opposite side, and I can also go there. And how about the next one? Well, I think you see where this is going. So, in terms of the movement, what's true is that a semi-queen on a toroidal board can do the following. It can move any amount horizontal, any amount vertical, and whatever number it's currently on, it can go to any cell with the same number. Because that's moving in that diagonal fashion where we allow wraparound. And at this point, you're like, isn't this just our normal board? And the answer is, it is just our normal board. Exactly. So that's why there's this nice connection. And so it's sort of a really beautiful, nice result that there's this fun problem that had been explored independently of juggling. People really hadn't necessarily made the connection, but it turns out that we were all looking at sort of like the same kind of thing. Hey, I want to know, how many ways are there to rearrange this? Oh, well, I want to talk about ways to put down these sort of non-attacking strange pieces on a strange board. Like, great, let's get together and have a party. Sounds pretty good. That sounds like what math is all about. All right, so lots we don't know. There really is lots that we don't know. But it's nice to know there are still problems for us to work on, still things for us to do. And of course, there are still more for us to talk about, and so we will continue again. See you later.